Okay, class, can you hear me clearly? If yes, give me a thumbs up. Class, can you hear me clearly? Okay, or can you see the screen clearly? Okay, hold on. Let me share the screen. Hold on. Share the desktop. Okay, class. Okay, gentle reminder. We're going to have a midterm test on 10th of August. Okay, so the test you're going to take about 1 hour actually. So you need to submit it to me to Weber, or you need to do scanning lah, or photo taking out. That will give you half an hour. Okay, so basically is now, you know, tentatively I decided to put it chapter 1 and chapter 5. We're going to start chapter 5 next week. So make sure they understand everything in chapter 5 next week. Okay, so anything you are not happy with this? Okay, so I repeat, we're going to have 1 hour plus. I'm very nice one, you know, because that day we have 2 hours, correct? 12 to 2. So, and then during the midterm test on 10th of August, everyone need to switch on the video. No, you cannot run away. I want to check. Are you sure you are alone? Nobody at your back or super intelligent people behind you to guide you. Correct or not? I want you to do it alone. Okay. So now at that time, I want to see whether you are a boy or a girl, a male or female. Okay. So is it okay, class? Is it clear? Is it everyone in already? Let's check how many of you now. Okay, it's 32. So is it okay, class? Any questions? Any questions? Wow, if behind got something not very scary, I got a special eye. Okay, you never know. Probably your ancestor, your great grandfather helping you. All right, if this happen, I will put all the cross all the Buddhist things or everything so that they will go away, not at your back, you know, to back you up. Okay. Okay, Kai Chin, I hope that you know what I mean. Okay, class, if all these are clear, then we should begin our today's class. I try to finish all the lecture, all the real-time operating systems. Okay, where are we now? So any questions? Any more questions? If no, let's begin our class. Where are we actually? This one, is it? So class, last week we talked about semaphore, and then so we talked about semaphore. So basically, semaphore is majoring in signaling. However, we got binary semaphore. Binary semaphore is also allow you to have protection. So it's like for, let's say we are sharing one critical region, or sharing one memory address, or sharing one involve a critical region. So that's where we use a binary semaphore, only one. If we have more than one sharing resources, 10 or 20, we can using a counting semaphore. Okay, it's like a counting semaphore. Okay, so we also got something called mutual exclusion or mutex. So mutex is basically is a locking mechanism. Again, don't confuse now. Tentatively, just assume that binary semaphore and mutex are similar, although they are not similar. So still remember that there towards the end of the class, someone asked me, and I explained. How did I explain to him? I explained such that one of the example is this. I explained to him like semaphore. Normally semaphore. This is a key. Sorry, my drawing is very ugly. This is a sharing resources. Let me change the. Where is the pen? Why cannot get back my pen one? Yeah. Okay, now mind. So these are the sharing resources. Sharing resources. So if task A get the key, then my semaphore count is 1. Then task A is finished. He released the key. task B can take the key over here. Okay, so this is like one of the example of semaphore. So semaphore, he will release. No matter he finish, he will release. But one of the features of mutex is same like semaphore, but he got a locking mechanism. Like example, I take the key, account is 1, I take the key. So I take the key, then account becomes 0. My lock count is become 1. So let's say when I finish, my task A is finished. So task A has a right, to keep locking it. I lock the count become 2. And this seldom, never happen in semaphore. Semaphore finish, you release it. So that's why mutexes is like locking mechanism, can lock it. Okay, other than that, more or less it's the same. So sometimes mutex also build in priority inheritance and to solve the priority inversion problem, which is called priority inheritance. Okay? Okay, or not, class? Okay. Is it okay? Is it clear? So, and towards the end of that round, we also come up with example of a nuclear reactor. So when the nuclear reactor in here, we are controlling a temperature inside this nuclear reactor, and a control by the console. A lot of things is being controlled. So here we can decide which one is low priority, medium priority, high priority. So how to decide which is high priority, which is medium priority, which is low priority? So these questions we will answer it after this. Okay. And then we have a semaphore, we got a queue, we got to control all these things. I believe those who already attended this this morning's lab, okay, you basically understand already what is queue, what is semaphore, and what is task, correct? Because we also review all this, in MicroCOS2 as well as in FreeRTOS, okay? So, but semaphore will lead to few problems. Starvation. Starvation means you are the one that keep on owning the things. So then, if this is really happen, it's your problem because you design the program lead to starvation. Okay. So we also got deadlock. We also got priority inversion. So deadlock can be solved by order of locking. I told you like that day, correct or not? Okay. So and we also discuss something called priority inversion. And you see, if your MicroCOS2 using pen and post, pen means we are desire you want the semaphore. Post means we are releasing the semaphore. So basically, this one in FreeRTOS this morning ESP, this is take, this is give, correct or not? Correct. Post mean give up. Okay. So releasing a semaphore. So whenever this thing is happening, it might cause a priority inversion. Let me clean this first, class. Sorry, it's so messy here. Let me clean all this thing. Clean. Okay, like in this case, we have. I just repeat what they mean by priority inversion. Let's say, for example, we got 3 tasks. Task 1 is highest priority, medium, lowest priority. Task 3 in charge now. Okay, why task 3 in charge? Because at the very beginning, task 1 is in delaying mode. Let's say, still remember this morning, those are running. Let's say this is already start with OS time delay. Okay, he's delaying. So we're delaying, he's nothing to do lah. So this also delaying, nothing to do lah. So task 1 doing something lor, which is lower priority. Very chaman ma. Those your normal worker will do more things. So suddenly do halfway. Okay, task 3 want to use the sharing resources to get the semaphore. He using the semaphore. Then suddenly your big boss who is high priority coming in. Okay, he's doing his own work, but at this position, he don't want the semaphore, means he don't want to use the sharing resources. But however, at this position 4, he want to get the semaphore. Cannot. Why? Task 1 is not yet finished. He's still in the middle of using this semaphore. Okay, so he can't. So task 1 have to wait. No matter you like it or don't like it, he has to wait. Wait lor. Wait. Okay, then coming back here, task 3 continue doing his job, on this semaphore. Then worse, then the middle priority task interrupt, and do other things. He don't want the semaphore. He do other things. So in the end, task 1 waiting for semaphore, isn't it? He can't wait and wait and wait and wait. Then only after task 2 is finished his work, where he don't even need the semaphore, then he pass back the task to task 3. Task 3 completed it, then only he release the semaphore to task 1. So task 1 only can take the key to open the door to use the sharing resources. So at this moment, this is what we call priority inversion. For your information, the Mars rover, so class, if you're interested, you can step back after 6 o'clock. Okay, if those are class, you can leave lah. It doesn't matter. I just bring up, because today is a big day. Why is a big day? 7:50 later, in US, NASA going to launch his Perseverance rover, to the Mars. Okay, so today is an interesting day, and some more we are discussing about Mars rover. So that's why I take this opportunity to trigger some interest, where for information, I really like to understand what is space. When I'm young, I'm curious about space. I'm curious about all the stars, all the galaxy, all these things. Okay, so it's a good time to share something on the Mars rover. So this is the same thing. So due to, like for example, in Mars rover in 1996, the first Mars rover is sent by US to the Mars. They create this problem. So once this priority inversion happened, and they got watchdog timer built in here, what happened? If they got watchdog timer, he after wait cannot restart. The whole system is restart. So your robot, the rover is in the Mars. Due to this situation, until here, it keep on restart, reset because of watchdog timer. What happened? Then everyone panic in the ground. Okay, you know what operating system they're using at that time? VxWorks. So everyone is panicking. What is happening? For information, the NASA engineer software team took about 1 week to solve this problem. Then only they will program this. Okay, it come out in a newspaper. I will share with you. So this is the problem of priority inversion. Priority inversion cannot be solved 100%, but we can reduce it by using something called priority inheritance, like here. So when task 3 running his thing, I take the semaphore. So immediately I take a semaphore, task 1 take the priority, want to run it. Whenever task 1 want to take the semaphore, he realized that that semaphore already taken up. Automatically, the system will tentatively raise its priority so that task 2 don't have chance to interrupt. Okay, class, I'm talking like this, it looks very easy. But when you put in terms of programming, when you want to change the structure of the operating system, there's a lot of things involved. Of course, I'm not going deep into the coding, how do they do it, but I just let you know that they got such thing called priority inversion. So with this method, what happened? They will reduce the priority inversion. Immediately he finishes up and pass this back to the task 1. At that moment, this will go back to lower priority. So after it's finished all this thing, task 2 can interrupt coming in. Okay, to continue, task 2 continue to run. Okay, so that's why this is the difference between task 1 and task 3 in terms of priority, solving the priority inversion. Okay, it reduce it. You compare just now, so long. See, so long, just now. Okay, where is it? Quite long. Because due to this lengthy duration, if you don't set the proper watchdog timer, you keep on reset after reset, the whole system is reset. Okay. So let's move on. Okay, let's have an example. Let's draw it now. Okay. So again, this come out in the exam before those days. The following is the pseudocode listing for the 3 tasks created by the preemptive priority-based RTOS. When the kernel starts, the system clock tick is 1000 milliseconds. So the total, okay. The priority level are assigned task A, task B, task C. So basically here, Okay, task A, task B, priority lah. The event, my event is set by an interrupt switch routine. Is the first set at 950 millisecond after the countdown start. The semaphore, my sem, is used to control the access to a shared resources used by task A and task C. Okay, draw the execution profile from the instant of the countdown starts till 2000 milliseconds. Assume that context switching and system call takes 0 time. So he asks you to draw the execution profile, okay, timing. So let's draw it. Let's draw it first without using priority inheritance. Okay, so these are the program. Lah. So look at the program carefully. Okay, so basically this one is the highest priority, this one is the medium priority, this one is the lowest priority. All right lah, yeah. Lowest priority, highest priority. So priority level C is the highest priority. So this is like this. So at the very beginning, task C is waiting 950 milliseconds. So now let's draw the profile timing. Let's draw the profile timing. Okay, why I can't access my how to move this down? Why can I move this down? Just give me a minute, because I need a few colors so that you're okay with. Why can I move this down? Is it open too many? Okay. Okay, let's continue. Where is it just now? Oops. Now. Okay. 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 Let's draw the profile. Okay. So let me arrange a little bit. So we got 3 tasks here. Sorry for my yeah, not strict. Okay. Sorry lah. We got 3 tasks. So we got task A, task B, task C. Okay. So let's look at this. Task C is the highest priority. Wait for an event 950 milliseconds. So after 950 milliseconds, then only he do it for 30 milliseconds. No matter whether you like it or don't like it, definitely I put in black color. After okay, put something here lah. After 950, this must be 950 milliseconds. Then he do something on 30 milliseconds. Okay, so this is the highest priority. But in here, who run first? Task A run first or task B run first? Of course, task B will run first because task B is the medium priority. You do work for 700 milliseconds. Okay. Okay, 700. How to draw? Okay, 700 milliseconds. Okay, I draw like this, 700 milliseconds. Okay, so after 700 milliseconds, he delayed for 280 milliseconds. So when he delayed 200 milliseconds, task A will take over and do work for 200 milliseconds. Context switching, OS time delay ma. Context switching over here, task A will do for another 200 milliseconds. So I put what color? Okay, this color. So where's my? Okay, continue here. So we come to here, this is a bit 200 milliseconds. Means 700 plus 200, this is 900 milliseconds. Okay, so at that moment, task A acquired the semaphore. You take the semaphore. Okay, you take the semaphore. You take the semaphore, you grab the semaphore, but he wants the semaphore to do things for 70 milliseconds, but he can't. Why? He just able to do until 950 milliseconds because you take over by task C ma. Right or not? So then come back to task C. After doing 30 milliseconds, he wants the my semaphore. Cannot law. Why? Because the semaphore still owned by task A. Task A haven't complete yet. Task A just run for 50 milliseconds only. Correct or not? Only 50 milliseconds. So what happened? Then you switch back. Will you switch back to him after 30 milliseconds? Will you switch back to him after 30 milliseconds, class? Yes, tell me, class, come on. Will he come back to here after 30 milliseconds? This is logic. Yes, my dear, all of you, are you participate? Why so quiet? Call someone. Where are you? Why nothing? Nobody posts anything. Yes, class? Why so quiet? My question is, after this 30 milliseconds, will task A continue or task B continue? Class, keep this. Okay. Yes, anyone from class, are you following? If yes, give me a thumbs up. I can't see thumb means nobody following, is it? Are you sure you're following? Only one, my God. Okay, so class, I try to repeat. I repeat. Are you sure you're all following? Only two. Class, I repeat. They got three tasks here. Task C is a highest priority, a lowest priority, medium priority, highest priority. So based on these three things, at the very beginning, task C wait for an event. When while waiting for an event, the kernel are very intelligent in micro-COS2. Now you're waiting, waiting, let other tasks run first. So now just remaining is task A and task B. So task A and task B, who is higher priority? Of course, the task B are medium priority. You run first. You take up 700 milliseconds. Team already done. But is it task A take over? No, task A waiting, you know, we will take about 950 milliseconds. So not 950 milliseconds yet. So that's why task A you take over, you do 200 milliseconds. 700 plus 200, just 900 milliseconds. It's not even reach 950 milliseconds. Whereas task B will delay 200 milliseconds. Okay, it's still delaying. So then task A will continue doing his work. So then he needs a semaphore. He take the semaphore, he take the sharing resources, and he do work. He needs 70 milliseconds to complete this semaphore. So after 50 milliseconds, he can't continue. Why? Because task C, or who is a higher priority, already reached the time 950 milliseconds, then he need to take over. Then that's why he take over. So that's why task A stopped whatever he did, whatever he do, okay, under the semaphore, under the sharing resources, task C will take over. Remember, this is only single core CPU, not ESP32. So you take this. After 30 milliseconds, he said, I want the semaphore. Can you take a semaphore? Cannot, cannot take the semaphore. Okay, so will he pass back to task A? The answer is no. Why? 700, 200, 7 plus 200, 900. So over here is already 280 milliseconds, correct or not? Already passed. So this means that task B, medium priority, will take over and continue his big job. Okay, he'll take about 700 milliseconds. 700 milliseconds, you know. Then only he release. This will repeat. Okay, to work for 700 milliseconds, correct or not? Okay, doing out 7 milliseconds, then only we will release, probably you release, then you go back to task A. Okay. Okay, task A will take over, continue another 30 milliseconds to finish his task. Then only he passed back to this beautiful thing and continue taking his semaphore and doing another 50 milliseconds. Class or not? So this area here is what we call as a priority inversion. So what is the time? It's about 700, and this 20 or 20, this one 20, 20. So it's about 720 milliseconds. The priority inversion is about 720 milliseconds. So you got what I mean in that class? It's about 720 milliseconds in this case. So this is not what we want. So therefore, if you are using priority inheritance, this case wouldn't happen. Okay, let's look at the priority inheritance. How priority inheritance solve the problem? Oops, I go back here because yeah. Okay, okay. Priority inheritance. So let's look at priority inheritance. How priority inheritance solve the problem? So as usual, we got 3 lines here. Okay. Yeah, never mind lah. So task C, task B, task A. So task A who run first, task B run first, task B take about 700 milliseconds. Okay. Millisecond. Then this will run for 200 milliseconds. Then you take the semaphore, which is 50 milliseconds. Okay. Okay. Take the 50 milliseconds. Then only here this will run for 30 milliseconds. One the semaphore cannot get. Okay, cannot get a semaphore. So automatically it will raise the priority of task A. Task A by right, this is the lowest priority, is medium, this is highest. Raise it, become highest, so that task B cannot interrupt it after 280 milliseconds here. It cannot interrupt it and let this continue to finish his another 20 milliseconds. Then only he come back over here, let it take the semaphore for another 50 milliseconds. Okay, so the priority inheritance is just, the priority inversion is just 20 milliseconds only. 20 milliseconds priority inversion. For compare just now, 720 milliseconds, correct or not? So this is the beauty of priority inheritance. Okay, how to do it? Okay, so this give back to the operating system. So operating system will manage this. Okay, operating system will manage this. There's something called, so, like for example, like probably FreeRTOS already built in this intelligent system. Okay, to solve the priority inversion and priority inheritance problem. Okay, is it okay, class? Okay, let's move on. So then, of course, they got another way. They call it priority ceiling protocol. So due to this problem, some of the real-time operating system, have a feature called priority ceiling protocol. What is priority ceiling protocol? Before the higher priority want the semaphore, he automatically raise his priority. You understand what I mean or not? See, task A only raise his priority when other higher priority wants a semaphore. If using ceiling protocol, automatically, whenever I take the semaphore, whoever take the semaphore, I already raised my priority to the highest. Okay, regardless whether task C eventually won the semaphore or not. Okay, so there's two different things. Priority inheritance, whenever people need that particular semaphore, then only the lowest priority task will be raised. But the priority ceiling protocol, he will raise automatically when he takes a semaphore. Okay, just as simple as this. I'm not going through details, because it involves some mathematics here, so I'm not going through all the mathematics. Just to briefly let you know that it was something called priority ceiling protocol. Okay, so okay, so any questions so far from the class? Any questions? Any questions? Am I going too fast? If no question, can you give me a thumbs up? Since funny picture just now, not many, only 1, 2, 3, 4. I'm so sad. Is it okay? Who cannot get it? If you can't get it, please give me, just switch on the mic and ask me questions. Okay. So any questions? What is this tree baby? Okay. Okay, any questions? No questions? Can I continue? Okay, I need few more. Yes. If you understand, I will continue because priority inheritance is such a very important thing. Okay. Okay, very good. I see all funny things. Okay, where is where is that? Again, I forgot his name. Where is that Kampa fellow? What's his name already? I don't know. I keep on forgetting him. Okay. Oh yeah, Yi Chuan, are you okay? Okay. Okay. If everything okay, then we should continue. Okay, we should continue. Okay. So we got new taxes. Okay. Again, in Microsoft US2, they give you new taxes for information. New taxes, may build in, the features to solve the priority inheritance or priority for the problem of priority inversion. Okay, so the crude way of solving all this, I told you already, enter critical, and exit critical means this is disable the interrupt, this is enable the interrupt. So it's, I don't know, this is not very recommended lah. So it's the crude way. Okay, it's a crude way to solve this problem. If you're lazy, you think that it won't create any problem, yes, you can go ahead with this. Enter critical section means disable the interrupt. Exit critical section means disable. Enter critical section means disable the interrupt. Exit critical section means enable the interrupt. Okay. Okay. So priority. So class, keep this in your mind. If priority is assigned arbitrarily, the benefit of real-time operating system may be not realized. When multiple tasks have important deadline, assigning priority can be particularly difficult. Like in your task, in your assignment 1, which one is the highest priority? It's a very difficult question. You as a user, you as a designer, you should monitor all these tasks, which one is critical, which one is less critical. Although you cannot simply just monitoring, you need to do some mathematics, you need to identify a lot of things. So class, I just sharing with you the most simple methods. There's a lot of complex algorithm behind priority, a lot of mathematics is involved. So now, as we are just a beginner, so I'm not going to something very detailed. Okay, so there's many methods. Okay, but before that, you must understand we got soft real time and hard real time. Remember this. Okay. So then we start with something called Gamma criterion. So Gamma criterion gives you two things. Is it very critical? Is it very urgent? If both is no, if not urgent, it's not critical, lowest priority and put as. If this is very urgent, is critical, lower. If both urgent and critical, highest. If it's just urgent, it's not critical, it's higher. Okay, so this is the thing, that you have to considered in the gamma criterion. Okay, so in the gamma, so remember, normally if the highest priority, the task execution rate should be higher lah. Okay, because it's urgent. Okay, it's very critical. So more times, it being executed. Okay, so there's another way they call rate monotonic scheduling. So rate monotonic scheduling is very interesting. So he said that he put the task with highest rate of execution to be the highest priority. The fastest rate at the highest priority. Okay, so these are the special case of a gamma criterion. The task with the highest frequency, highest priority. So, but there is something that you need to be alert, such that all the tasks need to be run periodically. This is need to be considered under the rate monotonic scheduling. You only can use RMS if each task is run periodically, and the task already let you know, a task always complete its work within a fixed amount of time. So in this fixed amount of time, that is have to be completed, and these tasks cannot be interact. Just like your assignment 1, task 1, task 2, task 3 are not talking one another. Keep this in your mind. If you got inter-task communication, like we need to have like signaling, all these things, probably RMS is not very accurate. Okay, so before you look at the RMS, let's have a look of this example of media player. Like you can label sometime, like user interface. Is it urgent or critical? For me, it's just an urgent. It's not critical. Okay, media player, media player. Media player, you got video decoding, all these things, correct? You play MP4 file, you play what? Like MP4, MKV, using a media player, inside got circuit do a lot of decoding, correct or not? So like video decoding, this is critical. Video output is just an urgent thing. So like this is urgent. So this is critical. So can you tell me which one is critical, which one is more important? This section or this section? Video is more important than audio, or audio more important than video? The answer is what? Okay, you go and think about this. Video or audio, which one is faster? Okay, you go and think about this lah. So that's why whenever you do any project using real-time operating system, you have to decide. You have to know which one is urgent, which one is critical. Okay, so let's look at the RMS. So we come back to the RMS. RMS have a very simple formula we're going to use. Okay, so look at here. So always remember, tasks do not synchronize one another. So there's no inter-task communication. Keep this in mind. So according to the RMS, this formula needs to be abided. Okay, Y is the maximum execution time, T is the execution period, N is the number of tasks. N is the number of tasks. So in order to abide the law of RMS, these have to be greater or same with the execution time divided by the execution period. Okay, you might be don't know what is this, but it doesn't matter. You look into some example later. I can guarantee that you can understand. So according to RMA, if you got infinite number of tasks, eventually you have to put it ln 2. Is 0.693%. So this means that you are not utilize your CPU 100%. So yes, it's true that some non-critical tasks, the system, you can use 100% of CPU time. But if you follow RMA, if you get infinite tasks, maximum is just 0.693, means 69.3%. Okay, only 69.3%. Okay, without delay, let's look at an example. This example will clarify a lot of things. Okay, this is the total time of execution. This is the execution time. So in every time he repeat 5 milliseconds, and he completed in 5 milliseconds, but the period is given is 30 milliseconds. He can complete it in 3 milliseconds. The total period is given is 10 milliseconds. So the utilization is just 5 divided by 30. The execute is 3 divided by 10, 4 divided by 15, according to the EI over TI formula. Okay, so you get all this value. So based on my calculation, this is 0.167. 3 over 10 is 0.333. 4 is 0.267. Okay. So, and based on here, the longest execution, the longest period, according to the formula, remember he said that where is it? He said that where is it? The highest rate of execution is higher priority. So which one is highest rate? The highest rate is definitely is 30. So this is the highest rate is which one? Highest rate. Which highest rate is which one? Highest rate is which one? So it's 10. Highest rate is 10. So this is the highest priority. This is the medium priority. This is the lowest priority. So the execution rate. Okay. So this will be 1, 2, 3. Okay. Let's add this thing up. This is the summation of this is equivalent to 0.767. So class, doesn't matter if you don't understand now. After you go through this example, I can guarantee that you understand. So based on the formula given, the utilization, U is the summation of the 3 from n equal to 1. So basically, is it greater than n 2, 1 over n minus 1? We got 3 tasks here. So it's 2, 1 over 3 minus 1, you got 3 tasks 3. So this is equivalent to 0.78. So definitely it's greater than 0.6767. So this means that the RMA criteria can be met. Okay, this is one of the example. Okay, so this means that it can reach, it can be met. So the system is fine if I assign task 2 as a highest priority. Do you know what I mean in our class? Okay, so actually, okay, let's come on with another example. Let's come up with another example. Okay, so this one. So what is the utilization? It's 12 divided by 50, 10 divided by 40, 10 divided by 30. So this is 0.24, 0.25, 1 over 3, 0.333. Summation here is about 0.82. So the priority, this is the highest priority. This is the second highest priority. This is the third priority. So basically, is it greater than 3, 2 over 1, 3 minus 1? This is equivalent to 0.78. So this is failed. Okay, why is failed? Let's draw it. Okay, let's draw it. We draw this first and see what is happening. Okay, let's draw it. And now I'm sure that you understand after I draw this, the task. We got task 1, task 2, task 3. Okay, let's begin with the purple color. So the task 1, the completion time is 50. Okay, each section is just 12 milliseconds. The completion is 12 milliseconds. Okay, so I start now. So each one is the highest priority. Task 3 is highest priority. So task 3 will run first. Task 3 will run first. Highest priority, medium, lowest. Okay, task 3 will run first. So task 3 will run. It take about 10 milliseconds and is completed in 10 milliseconds. Done already. Although it's given 30 milliseconds, but it completed in 10 milliseconds. Okay, so it's working. So then this will follow by class. Please look at this carefully. Then task 2 will run. Task 2 will only take 10 milliseconds. Again, it's completed. It's completed. 10 milliseconds is completed now. 10, 20 milliseconds. Okay, class, look at here carefully. So then, task 1 is running. Can task 1 run 12 milliseconds? Cannot. Why cannot? Because after 30 milliseconds, the process is repeated. So task 1 is not finished. The bubble means it's completed. Completed. Task 1 cannot. Why? It just can run 10 only because the process is repeated after 30 milliseconds. So the process is coming back to task 3. Task 3 will coming back again, for another 10 milliseconds. Then it's completed 10. So I draw this line down here. This is 30 milliseconds. 30 milliseconds is repeated. Okay. Then it followed by the blue color one. 10 milliseconds. Okay. So 30 for okay. 30, 40, 50. So it's 50 here. You see, it is already 50 milliseconds. So after 50 milliseconds, my task 1 is not even completed. So this means that it's a failure. This is a failure. I cannot simply assign task 3 has the highest priority. Do you get what I mean or not, class? Do you get what I mean or not, class? You see, after 50 milliseconds, I can't. My task 1 not even completed. So this means that my RMA prediction is correct. Okay. Is it okay or not, class? Class, is it okay? Okay. Let's have more example. So remember this one. Let's draw this. Let's draw this. This is the 35, 3. This one is working. This one is working. You draw. All of you try to draw this. Is it working? Is it really true? Can it really abide the law? Okay. 3, 1. Okay. So we got task 1, task 2, task 3. Task 1 is the highest priority, correct? Task 1. Task 2 is the highest priority, correct? Task 1 is the highest priority. So task 1 run first. Task 1 just take about 3 meet the deadline. Then this one take about 4 meet the deadline. 3, 4, 7. All right. 3, 4, 7. Okay. Then task 1, 3, 4, 7. Task 1 here, I just can run 3 only, correct? It's not completed. Why? Because task 2 is coming in. It's already 10 milliseconds. So then this will continue running another 3 times. This will continue running another 4 times. All right. So 3. So after that, you got 30 milliseconds, very long. So after that, you can finish it another 2 times over here. So it completed. So if you reach, so this method is no problem. So I can assign the assignment that I did just now is perfectly all right. Is it okay, class? Is it okay, class? So I hope you got what I mean. So this means that IMA is very good, if you know, of course, you need to know the execution time. The total period is given to them. Okay, within this period, you have to finish your job. Okay, how long do you need to be run? Okay, so remember, this is what the IMA conclusion. The system meet the IMA limit and is guaranteed to meet all deadline. We say that. IMA provides a guarantee that system obeying the IMA condition will always meet the deadline. It does not say that system with higher utilization will not meet the deadline. He didn't say this. Okay. It is seldom possible to apply it exactly because most of the systems do have inter-task synchronization. I told you already. So in assignment 1, I always stress that they don't have all these 3 modules you did in assignment 1, they don't interact one another. But if you got interact one another, you need to use post, pan, all these things, signaling, so to make sure that the thing going smoothly. So in practice, it's a good guide. What is the reasonable system? So IML limit, if the IML decrease monotonically, and then normally if you got unlimited tasks, then always put that is 0.693, 69.3%. Okay. So as a rule of thumb, RTOS with many tasks should never run with utilization higher than this limit. Okay. So remember this, cannot higher than this limit. So this is why this limit is based on their mathematical calculation. If you're interested, I can give you the paper, you go through it. Okay. So if the IML limit is not met for a given application, the solution is either to use a faster CPU, possibly reduce the number of tasks. Correct or not? So just now, still remember just now we couldn't meet this, we couldn't meet ma. So what should we do? Reduce the task or increase the CPU speed or. So this is the only solution they are proposed. Okay, let's have a look of another questions. Okay, let's have a look of this. This is even more interesting probably. Okay, can you draw this? Can you draw this? Okay, can you do this? So the execution time, the period. So this is 40 divided by 80, 0.5. 10 divided by 40, 0.25. 5 divided by 20, 0.25. Class, of course, you need to know the task that you are running, or how long it can execution's time is done, and what is the appropriate period is given to you. These two things you need to identify first. So based on here, which one is higher priority? We look at the period of time. So this is the highest priority, medium priority, lowest. So highest I put 1. Okay, this is 2, this is 3. Okay, so let's draw this. Okay, sorry, why is how to draw streak? Xin chai lah. Okay, so who start first? Over here, the highest priority will start first. Let's take about 5 and can about 20 milliseconds. Okay. So completed. 5. Then followed by 10.
So the priority is C by highest U.
Here, this one T. The 20 millisecond is the highest. Okay, 40 is the medium, T is the lowest. Okay.
Oh, okay. Thank you, sir.
Yeah. So this is task 3. This is task 2. This is task 1. Okay, then let's draw this 3. Then it take about 10. Okay, I just use one color. I'm lazy to change. Completed 10. So then 15, or it's about 20 15, or I just allowed another 5 only. 5, not completed 5. All right. So then I will come over here. Okay, but before that, just now I haven't worked it out. Before that, sorry, this one 0.5. The summation of this is what? Is 1. So 1, this is 3 tasks, 2 or 1, 3 minus 1 is 0.78, correct? So definitely it's not lah. It says it's not, you know, it says it's not, okay? But you still need to finish the profile drawing. You need to finish the profile drawing. Okay, then this already 20 lah. 20, so the process is repeated now. 5, 10. So 10, 5. Okay, now because this haven't expired yet, this one got 40. This is just 25. So you give back over here. This can run until how long? This can run until 15. All right. Now it's 40. All right. So 40, 20, 20. All right. Then this will be run again for 5 times. This will run again for 10 times. This will repeat again for 5 times. Okay, so this one is already 60. Am I right, class? Do I make any mistake? Right, correct or not? Do I make any mistake? Yeah, correct. Yeah, correct. Okay, correct. Okay. So I don't make mistake. So this will be repeated again for another 5 times. So this will give you another 15 times. So in this case, you can find that is 80, 20, 25, 40. You meet the deadline. You meet the deadline. You meet the deadline. So what we can conclude here, although it failed the utilization, but it successfully meet all the deadline. So this means that all process that pass the test will schedule successfully. However, those fail the test may schedule successfully also. This is what I want to bring it out. So this means that drawing the profile is more important. They can show that, you know, can show that it also success. Okay, you understand my point or not, class? So in this case, what they can see, it failed the utilization test, but it successfully meet all its deadline. So what does it mean? If this system, this means that all the process pass the test will schedule successfully. Means it pass all this, is guaranteed schedule successfully. But however, those who fail the test may schedule successfully also. That's why you need to draw the timing profile. So do you got what I mean or not, class? Okay, so this is what it mentioned over here. It does not say that the system you hire will not meet the deadline. It doesn't say that. Okay, you still have to draw it out. Okay, so this is a very unique sharing. So I can write like this. So even though I fail the utilization test, but it successfully meet all the deadline. Okay, so this means that all processes that passed the test will schedule successfully. However, those fail the test may may 100% may schedule successfully too. Successfully also. Okay, do you know what I mean or not? Okay, so this means that those who are fail, okay, you need to draw it out. So those who are success, it guarantee you success. You know what I mean or not, class? So this is what you want to bring out, in the RMS rate monotonic testing. Okay, class. Okay. Okay. So any questions, class? Any questions? Any questions? The priority is depend on the T. Okay, the total periods is not D, not U. Okay, not the utilizations. Okay, it's the T. Yeah, it's the T. It's the T. Okay, okay, highest rate of execution. Okay, it's a T. It's a T. Highest rate. Okay, it's a T. Which is the highest rate? Of course, shorter period is highest rate lah. Not the highest value. Highest value means lowest rate. English. Highest value means lowest rate. Lowest value means highest rate lah. Faster correct. Okay. Okay, this is the highest. Okay. So class, any questions? Class, any questions? Okay, class, if no questions, you may leave now. If those are interested, you can step back. I just briefly go through. I just very quickly prepare this slide. Every year I prepare this slide for the Pathfinder inversion. In 1997, this is the first rover that is designed. Okay, Weilun, no problem, is recorded. Never mind, those of class can leave now. I just briefly go through because today we have a countdown. I already start the countdown. Okay, where is my countdown? Where's my countdown? So we still got about 1 hour before the first launching, and you can watch it live. You can watch it online. Okay, so they're going to launch very soon. Okay. Anyway, it's recorded, doesn't matter. Okay, let me stop this first. Let me stop the recording and recorded it again. Okay, just for fun only, nothing is not coming out in exam. Okay, just for fun only. Let me stop this recording. So let me start back another recording. Louis Cheng Zheng is inside the rover. Okay, I don't know how you're going to do this. Okay. Very good. I love you. Okay, let's start the things. The problem of a rover. So just to share with you, NASA sending their first. What is that? I don't know. Okay. Look. Okay. Anyway same lah. So many Louis here. Okay. Anyway. Okay. Where is it actually, the first Pathfinder, is sending by NASA in July 4th, 1997. Okay. So since after that, there's a lot of things going on. Correct or not? So the most interesting is, of course, previously they're sending a lot of Mars Land Rover. They fail, is exploded, they're missing because Mars is something very far away. They got a lot of climate changes. Sometimes when they reach Mars, they couldn't land it successfully. Okay, it's not so easy. And where to land, what position, what time to launch it is properly calculated, because they need to launch it at this time so that they can reach Mars on this date where there's no storm or something. Okay, so that the climate is successful. I mean, they already do a lot of calculation and studying. Okay, so they can reach on time. So interesting of this perseverance, because they're really planning to bring back something, to our Earth. So far, it's never happened. You might probably you watch a lot of this alien movie lah. Something bring back, got disease, got alien coming out and eat the scientists. I'm not so sure that one. Okay, I don't know, but they're planned. You know, the perseverance to come here and dig a hole, get some rock. I believe you watch a lot of series. I mean about this. Then they drop it here. Then they send another rover. Then the Mars sample will return in 2026. You know, they're coming back, fly back, like orbited back. You know, just like their own rocket and coming back and reach to our Earth. Okay, so but basically, it's very interesting lah. So basically, the Mars Pathfinder is the mission is just to take picture those days. They're using a parachute, they're lander, they got airbag, and also they reach the Earth, correct or not? So they analyze soil, demonstrate the robot. This is started in Sojourn. There's so many, and successfully of this Pathfinder, they come back with a lot of pictures, and there are a lot of chemical analysis, rock and soils, but they never bring it back. All these things is analyzed on the spot, and they're using their wireless things and coming back. Okay, they're coming back to the Earth. Okay, but basically at the very beginning, the Mars Pathfinder, they're just a very low cost. I'm not sure nowadays, but those days, the first one is just cost about 150 million. And it's not the American itself. They are working together with different countries, like Russia, all these things, you know, those are interested with science. They're coming up with the proper funding. They invented all these things. But of course, those days, China also involved. But I not so sure about this round because there's so fighting between China and of course US. Okay, so of course the Pathfinder is sending to definitely go to the Mars and do analysis. Okay, so and after some time it will die forever. It will stop forever in the Mars. So this means that Mars itself now got a lot of junks, you know, non-environmental friendly I don't know a lot of junks in Mars, you know, who are die off. Okay, so this is some of the picture that is taken and some of the history They started with Russian in 1996. It's just orbiting only. So the first successfully is still in the July 1997, and the last successfully of the one we're going to study, the Mars Pathfinder, is just September, just few months only, then it's disappeared. Okay, so but however, what I want to say is the first Pathfinder they are using VxWorks real-time operating system. It's very simple. They're using IBM i600 processor, nothing to be worried about. And then it's just 128 megabyte DRAM and 6 megabyte of ROM. Just imagine this thing can landed, you know, basically landed in Mars. Just a very simple design. I mean, simple design is not a very powerful processor. Here are some of the outline, you know, of the Mars rover at that time. Okay, so you can have a look. So it's not very difficult. And then those mechatronics students are probably, I don't know, probably one day you are successfully penetrate to US and work in their team. You never know that. So basically, this is a Pathfinder. This is rover. Rover is here. So they've got solar and what. This is a rover. Okay. So the rover can come back and charge and do all the things, you know, all the information gathering So at that time, the Sojourn control system is just built with the Intel 8085. It's just a 8-bit microprocessor. It's very the rover and Pathfinder is different. The Pathfinder is the one who landed, then inside got a rover. So this is a rover. The information, the rover at that time is just controlled by 8085 Intel microprocessor. It's just 0.1 million instructions per second. They don't need about very, very high performance informations down there. Okay, so the rover is capable of autonomous navigation and performance the task, communicate the Earth to the lander. Okay, this is a lander Pathfinder is a lander. So it's a very simple design. Okay, it's happened in 1996. Okay, this is a rover. Okay, this is a rover A camera, you know, it's just very simple design. So the antenna is to communicate with the pathfinder and the solar. That's it. Very simple design. I believe that nowadays you also can build something like this for Megatronic lah. So camera is in front. This is in 1996 as for information. So, and at that time, the communication is, I'm not going through details on all these things. What I want to bring one thing in, because your embedded system design, is this VME bus. So VME bus is a Versa Modular Europa bus standard. So just like your computer, we got PCI Express bus, those that got Versa Local bus, got ISA bus, ISA bus. You know, your computer, you put in your slot one, the slot, so the PCI Express, correct or not? Okay, the VME bus is the longest surviving bus until nowadays. In most of the factories, they still use VME bus. If you don't believe me, you go and Google and see. VME bus is started in 1980s until today, it's still surviving. How, you just ask yourself, how many technology can survive so long? One of it is a VME bus. Okay, why there's a lot of message? Okay, why SSD based? Okay, you can check online lah. Okay, so these are the Pathfinder configuration. I'm not going through all these things. You know, then the one or the problem, the Pathfinder problem actually is a VxWorks real-time operating system, where they are created a big problem, which is a priority inversion, where he leads to the system to keep on resetting, because due to the workshop timer that installed inside. So I'm not going through details over here, because you want to go details, it's not as easy as you thought. There are so many things is involved here. That time they're using VxWorks. Okay, probably now people say that, oh, they are not using micro COS too. Okay, so but for your information, at that time, VxWorks already have a capability of priority inheritance. They just didn't activate it. Probably it's due to their marketing strategy. They want to make it faster or something like that. So this is the analysis that have been done, because you are not, I presented this for my computer engineering student last time. So I'm not going more details over here. Just what I want to bring back is, in the end, priority inversion is a big problem. So it can be actually solved by using a priority inheritance. Okay, so this will lead to the system is keep on rebooting by itself. That's what I want to say. Okay, so they come out in the New York Times, you know, in 1997, how they solve this problem. Okay, they reprogram it. Actually, this is true. This is published. Okay, from New York Times. There's a lot of paper also published about the priority inheritance in 1997. So, and they detail how they're able to debug the problem, how they're able to solve the problem of multiplexers. Again, actually, this also lead to deadlock. Deadlock means it keep on repeating, you know, keep on repeating itself. Then they create a lot of problem. So this is how the program looks like. I'm not going detail on all these things, just to let you know that. Okay, and you can find all these informations over here. Okay, so, and of course this one I just copy from the JBL. Okay, from the NASA website. This is the timeline. Just to share with you. I believe you already watched this movie. So this is what is really happening, you know, in, that's the, why you cannot play? Okay, just have fun, because you're all very tired already. This is the first one, 1997. They're using a board. No more happy, no more hugging this round. Social distancing. No more like this. No more happy. Because US is such in big mess. So with all this, for your information, the Perseverance, they designed it more than 10 years before they launched it. They tested it in the lab, for more than 10 years. Okay, and again, the whole system is written using C program. Okay. Okay, that's all. So, and for your information, they are already choosing the candidates for 2030 astronauts to go to the Mars. Okay, just to share with you. Okay, I just hope that Malaysia finally got their own team, one-man mission. Okay, maybe you watch a lot of movies, Okay, just really hope that Malaysia can have their own capability to start up our own stations. Okay, because we too rely on overseas on all these things. Okay, so again, all these things it just happened in the West. I'm not so sure about the East. So the rising of China and India is the key things that we should follow anyway. Okay, but still, all the technology, all the experience is still lies in the West, in US so far. So just wait for the moment, and then I'm not so sure whether this round they are successfully landed the Perseverance rover. Just for information, there's a lot of successful mission. There's a lot of failure mission as well, and it didn't show you all. There's a lot of how many billions or trillions US dollar is wasted because the rover not able to land on the Mars. Okay, so even Elon Musk rocket also exploded few years back, correct or not? Is a failure, correct? So again, okay, probably you can go and see how they launch it this round. Okay, so and its countdown is on. It's 7:50. It's still got another hour to go. Such a big event for, I don't know, probably not for all of you. So if you like study astronomy, all these things is very interesting. Okay, it's very interesting. Okay, So any other question? If no question, I will hang up already because I'm a bit tired. You know, today is quite. I already talked quite a number of hours. So any questions, class? Any questions? Yes, if no, then okay, bye bye. Have a great weekend ahead. Okay, bye.